The night sky is a deeply active ecosystem. These colorful structures are molecular gas clouds, vast stellar nurseries where gas and dust clump together until they ignite into new stars. A star's mass dictates the pace of its entire life. A star like our Sun burns hydrogen into helium over billions of years before cooling into a quiet white dwarf. In contrast, massive stars, those 10 to 25 times larger, are rapidly burning engines. They fuse elements with a frantic intensity just to keep their enormous weight from collapsing inward. This high-speed fusion creates a layered core. The star burns through carbon, neon, and oxygen, with each stage lasting a shorter time than the last. While hydrogen fusion might last 10 million years, the star will finish its supply of silicon in just a few days. Iron marks the end of the chain. Fusing lighter elements releases energy that pushes outward against gravity, but iron fusion consumes energy instead. When iron dominates the core, the outward pressure vanishes instantly. The star's internal balance is broken. Gravity, having been held at bay for millions of years, wins the battle in a fraction of a second. Trillions of tons of stellar material crash into the core and then rebound violently. This creates a supernova, a massive explosion that ejects the star's outer layers into deep space. If the remaining core is massive enough, the collapse continues forever. No known physical force can stop the inward crush. The matter reaches such a high density that it warps the geometry of reality itself. We are left with a black hole, an object so compact that we must travel towards its very center to see how our understanding of space and time begins to fail. If a black hole with the exact mass of our Sun replaced it today, Earth's orbit would remain unchanged. Planetary paths depend on mass and distance, both of which are identical in this scenario. The danger of a black hole lies in its density. All that mass is packed into a tiny area, allowing objects to get much closer to the center of gravity than they ever could with a star. At these close ranges, matter is exposed to extreme tidal forces. This diagram of an falling astronaut illustrates spaghettification. Because the gravitational pull at their feet is significantly stronger than at their head, the astronaut is vertically stretched and horizontally compressed into a long, thin ribbon. This physical destruction is driven by the extreme concentration of gravity. Matter is torn apart because a black hole's density creates a gravitational field that changes too rapidly for any solid object to survive. Approaching the center reveals the accretion disk, a flattened, swirling larder of gas and dust. This material orbits the black hole at relativistic speeds, heated to millions of degrees by friction and magnetic forces. The black hole's gravity acts as a massive cosmic lens. It captures light from the back of the disk and curves it over the top and bottom of the central shadow. To an observer, this creates the visual illusion of a glowing halo surrounding the hole. Relativistic effects also make the disk look lopsided. The side spinning toward us appears much brighter and bluer, while the receding side shifts red. This asymmetry is known as Doppler boosting. At the very edge of the disk lies the photon ring. Here, light is forced into a circular orbit by the black hole's gravity. Some of this light laps the singularity several times before escaping, creating a hall of mirrors effect where we see multiple distorted images of the stars. The glowing sphere we see in cinematic depictions is an optical illusion, a byproduct of light being redirected by broken spacetime. This photograph shows the event horizon, a mathematical boundary of no return. Beyond this threshold, the escape velocity exceeds the speed of light, trapping all matter and radiation forever. While it represents an extreme limit, general relativity still governs this region. For a supermassive black hole like M87, the gravitational pull at the horizon is actually weaker than the gravity at the surface of our Sun. Classical physics describes this boundary perfectly. The region where our known laws of nature truly fail lies much deeper in the dark. Past the horizon, the warping of space and time forces all paths toward the center. Even here, classical gravity dictates the fall, but that predictability is about to end. At the very center lies the singularity. This is a theoretical point where all the mass of the original star has been crushed into a volume of infinite density. Only here does classical relativity break. The equations produce meaningless infinities, signaling that we have reached a scale where we need a quantum theory of gravity to understand the physics at play. The singularity is more than just a location. It is the exact coordinate where our current understanding of the universe ends. Stephen Hawking realized that black holes are not completely disconnected from our universe. He calculated that they slowly leak thermal energy, now called Hawking radiation, causing them to eventually evaporate and die. This evaporation creates a paradox. While leaking radiation appears as random static, quantum mechanics dictates that infalling information can never be destroyed. Modern theories suggest microscopic wormholes link the interior directly to escaping radiation, ensuring the universe's data is preserved. Black holes force us to continuously rewrite the rules of physics. They serve as the testing grounds where general relativity and quantum mechanics must eventually reconcile, showing us how the universe protects its deepest secrets.
Right now, an invisible mass is currently tearing through intergalactic space at speeds over 2 million miles per hour. This is a runaway supermassive black hole. Its passage is compressing the gas in its path, triggering a 200,000 light-year-long trail of newborn stars. This discovery was confirmed using the golden mirrors of the James Webb Space Telescope. Pop culture often depicts these objects as inescapable vacuum cleaners, drifting through the cosmos and devouring everything in sight. But the data suggests a different role. By regulating starbirth and warping the passage of time, black holes function as the primary drivers of galactic evolution. Our own solar system is currently orbiting one of these giants. To understand why we exist, we have to look past the myths and examine the mechanics of how these objects actually operate. The name black hole suggests a literal void in the fabric of space. In reality, these are the most densely packed physical objects in the universe, forged during the violent deaths of massive stars. This diagram shows a star's core, where iron is accumulating. Stars stay inflated by balancing the inward pull of gravity against the outward pressure of nuclear fusion. However, fusing iron absorbs energy. When the core reaches this iron dead end, the outward pressure vanishes, and these gravity arrows overpower the core in less than a second. Trillions of tons of material collapse towards the center, rebounding off the dense core and blasting the star's outer layers away in a supernova. The remaining mass is crushed into a singularity, a point of infinite density, hidden behind the invisible boundary of the event horizon. This creates a gravity well so severe that it permanently breaks the physical rules that govern the rest of the universe. We often assume that falling into a black hole results in a fast, straightforward death. To see why that's wrong, imagine two observers, Jane watching from a safe distance, and Joe who is falling in. Jane witnesses the effects of time dilation. To her, Joe appears to slow down as he approaches the horizon, eventually freezing in place forever as his image turns red and fades away. From Joe's perspective, his watch ticks normally. But once he crosses the event horizon, his path through space collapses. Every possible direction leads only towards the singularity. This schematic illustrates the physical strain on an astronaut's body. Because the gravitational pull at the feet is significantly stronger than at the head, the body is stretched and compressed into a thin strand. This is the process of spaghettification. This encounter dismantles the body while simultaneously separating the individual's experience of space and time from the rest of the observable universe. Common wisdom suggests that black holes are eternal traps from which absolutely nothing can ever leave. In 1975, Stephen Hawking proved that black holes emit a faint glow of energy. This discovery meant that these giants actually leak mass and will eventually evaporate. This diagram shows the process of Hawking radiation. Pairs of virtual particles constantly form at the event horizon. When one particle falls in and the other escapes, it effectively steals a tiny amount of the black hole's mass. Over eons, this process accelerates. The black hole eventually shrinks to a point and vanishes in an explosion more powerful than a nuclear arsenal. This creates the information paradox. If a black hole completely disappears, the quantum information of everything it ever consumed is seemingly deleted, which would violate a core law of physics. The death of a black hole exposes a contradiction in our theories, forcing us to reassess the basic laws that define our reality. On a macro scale, we see these mechanics in action. This spiral galaxy rotates around a dark core, dictating the movement of billions of stars. Virtually every large galaxy in the universe is anchored by a supermassive black hole at its center, millions of times heavier than the Sun. This is the first direct image of a supermassive black hole. The glowing orange ring is the accretion disk, defining the event horizon's dark shadow. During their active phases, these giants release immense radiation. This energy pushes gas away, regulating the rate of starbirth and ensuring the host galaxy doesn't burn out too quickly. These objects act as the regulatory mechanisms of the universe. By anchoring galaxies and defining the limits of physical law, they make the structure of the modern cosmos possible.